All right, that was the Rubber Band Man from the mid-70s. Rubber bands will actually be relevant to this lecture in probably about 10-15 minutes, just a little bit. So started you off with something different from for a boring lecture. All right, so as I said last time, we were going over the syllabus. We're going to start with work, energy, and power. And so that's what we're going to be doing. So this comes out of chapter 14 from the text. So what I want you to look at is you have, this is typical positional plane, x versus y. And we have a particle that's going along a path here. And its initial position is a vector, r of t. And it goes a differential amount of time, so really short. And we get to this position here, r of t plus dt. We're going to make that a little bigger here. Bring that down. There you go. So, picture, so we got this particle going from here to here. So, in differential time, it'll move a differential distance, dr. And here's the force F. Okay, so we have a vector. We have another vector here. And we want to see what is the work being done to move from here to there. And so the external work are, and in this case it's differential work because it's over differential distance. dW is the external force, inner product or dot product with dr. So note, when we do this, we get a scalar. So all of this work with work, energy, and power involves scalars. Okay, that's a critical point here. Okay. And so what tends to happen in many cases when you integrate this, you get work equals plus or minus force times distance. But where does the plus or minus come from? Okay, over here. If the force and the positional change generally go in the same direction, it's positive work. If the force goes one way and the position changes another, that's negative work. So you can kind of think of this like your studies. If you work really hard and you get a bad grade, that's negative work. If you work really hard and you get good grades, so they both go in the same direction, that's positive work. All right, so we need to break this down some more. So I'm going to say let ds, where s is going to be path length. So if we go along here, we can start from some point and we'll measure s as a function of t. So that's the position, the path length as a function of t, not position in x and y, the length along this path. So ds, so the differential change along the path will simply be the magnitude of dr. dr is a vector. Okay, and of course the magnitude of F is just the magnitude of the force vector. Okay, so up here we had this inner product, so that says if we integrate dW we would get W, and that'll be the integral of F dot dr, which noting we have a dot product, we can replace that all by, from position 1 to position 2, F cosine theta ds. So this is a F, so we have basically, let's see, this here, oops. Let me take those bars out. I'm going to call F to be the magnitude of F. So this is the magnitude of the force, that's the magnitude of the position change, cosine of the angle between them. So you're used to seeing dot product is AB cosine theta, where A and B are the length of two vectors. All right, same idea. Okay, and we'll just note over here, S equals path length. All right, so we've seen that. Now, so if we analyze this just a moment, so let's see here, we have, here's that dr, and let's say this was the force vector F. All right, so here's the angle between them, and I'll drop down that projection. So what we get is work happens along this direction, but perpendicular. If you were to take this part, there's no work here. So what that tells you is that if the component of the force perpendicular to the path does absolutely no work, no contribution, it's wasted. All right? Okay? And so when we project this down, we'll note that along here we would get, let's just call it FT. So this is the tangential portion of the work relative to the path. All right, so we're going to analyze this more. So I'm going to note that here's this FT. If I was to sum all the forces along the tangential, that would give me mass times the tangential acceleration, which is, of course, just m s double dot. So this is the only force acting in the particle, so that's the summation of all the forces right there. So let's substitute this stuff in and see where we can go. So we have W, the work, going from position 1 to position 2, is F cos theta ds. That's where we were before. But F cosine theta is nothing more than this, which is then nothing more than this. So notice that you're used to integrating things with respect to time. We're integrating with respect to path length. It's different. All right, so I'm integrating acceleration not relative to time, but path length. How do you do that? Well, we need to analyze it a little further. So I'm going to note that the tangential acceleration, ds, because that's what that is, it's the tangential acceleration, is nothing more than the derivative of the velocity with respect to time, just like it's always been, and we'll add our ds here. Now, these terms are commutative, so I'm going to move this thing over here, and that leaves me with dv ds dt. The derivative of position with respect to time is what? Velocity. Okay? So now I'll just flip this order here, and I get v dv. All right? So I got to substitute that in. So it gets ever more interesting. So if I stick that in, let's see, we're just going to up here. And I'm going to have, now, I'm going to replace this ATDS with that. That means I'm now integrating relative to velocity. So I now have my velocity at the first position, my velocity at the second position, mass is still there, v dv. And I could have written v1 and v2 here just as well. Okay? Just emphasizing the relationship to path. All right? Once I have this, and in fact I should, in keeping it relative to path, let me call that s dot and ds dot. Okay? So if I integrate something relative to itself, then I would have here 1/2 m s dot 2 squared minus s1 dot squared, which, going back to velocity, we'd write as 1/2 m v2 squared minus v1 squared, or 1/2 mv2 squared minus 1/2 mv1 squared. So what are these things? We call these kinetic energy. You've seen this before. And all of this equals the external work. So let's see where we are. And that term external is going to be important later. We've got to get a few lectures in to make that clear why. But let's see what we have. So this is V2, so that's kinetic energy in the second state. That's kinetic energy in the first state. So I have this minus that equals that. So let's just bring this to the other side, and I would have KE1 plus this external work equals KE2. You've seen that before. And I think your book, though, writes this as, and a lot of people use the letter T, so we can call this T1 plus external work equals T2. You see a lot of both of these. I really couldn't care less which one you play with. All right, so there's the basic energy equation. Your initial kinetic energy plus the work you put into it gives you your next kinetic energy. All right, well, let's keep on playing here. I'll bring that back in a bit, maybe. So, now let's think about the work of gravity. Okay, so let's draw a little picture. So suppose I'm at initial height here, and I go up to an initial, a second height there. Okay, gravity is the force going down. So let's see what that means. If I go, if something moves from here to here, the work of gravity, which is going the other way, would then be negative. All right, well, let's see how that works out with the math. So the work from state 1 to state 2 is, I'm going from H1 to H2. The force is gravity, mass of our particle times gravity, which is going down, dH. Multiply all that out, get minus mg H1 minus H2, or, let's see. Oops, no, I did that wrong. H2 is there. H2 minus H1. Sorry about that. And so that leaves me with mgh1 minus mgh2. Now, what do we call these? These are called potential energy, and often we use the letter V for them. So here's PE1, and here's PE2, or V2. So, let's integrate this into the equation. So we started before, I'll just use the T. T1 plus the external work, okay, equals T2. And so I'm going to break out of this the work of gravity. So T1 plus, I'm going to use the V's over here. Okay, this is V1 minus V2. So I'm going to take the work of gravity out of this. So it's V1 minus V2 plus W external other equals T2. Spread that out, and we'll just note W gravity. Spread all that out, you come up with T1 plus V1 plus work external other equals T2 plus V2. All right. So, you've seen this before. So what are we kind of setting up? Kinetic energy plus potential energy at the start plus other work put into the system equals T2 plus V2. Now, let's take a look over here. If you notice, kinetic energy only depends on height, position. So, here's what we call this. We call this conservative. What does that mean? So consider some particle, and I'll look at this over time, and it starts here. So here's T1, here's T2. And it goes through all sorts of things, and it winds up over here. Okay? The path doesn't matter. Okay, this thing could have gone down here. and come up to there. All that matters is where am I here and where am I there. If energy is only dependent on position, it's said to be conservative. Okay? The work associated with that is conservative. So we have, this is conservative work because it's only dependent on position. If I get back down to here, it means I've done no work. Okay? And that makes sense. From a potential energy point of view, it's all derived by gravity. If I'm at the same height, I have the same potential energy. All right? So what we have here, we'll just, if this is these V terms, potential energy is always conservative if that's involved. So this, we can rewrite this now as non-conservative. So this is all the work, or if you come back to the same position, you're not back at zero again. Okay? So we have kinetic energy 1 plus potential energy 1 plus non-conservative work equals T2 plus V2. All right, what is the other standard conservative element from an energy point of view? Well, springs. All right, an example of springs, fairly good example, the rubber band man. Okay, so what do we have with a spring? So here's a spring coming off a wall, has a spring constant. All right, and we can send the path in one or two directions. This will be our 0 point. This will be the positive way, this will be the negative way. So if I take this spring and just, so this is, here it is unstretched, and I simply, somehow this gets to this position, what is the work of the spring? It's opposing that. So as I push this in, the spring the whole way is pushing back the other way. So to go from here to here is negative work. Now if I pull it out, the spring says, no, come back. So no matter what you do, the spring is kind of stubborn and it's going to do the opposite thing. Now, if you look at the force that's in this spring, you know that force is basically K times X is the usual. As I move this in some distance, S or X, I'll get a force going the other way. But anytime I come back to the same position, the force will be the same. If I get to here, the force is 0. This would be minus Kx. I can, if I get right back to here, it's the same force. This is dependent on position. So, we have F spring equals minus Ks relative to our path variables. So, W equals, from the first spring position to the second one, minus Ks ds. And I can integrate that directly, and I get minus 1/2 Ks2 squared minus 1/2 Ks1 squared. Okay. Plus. Sorry, because there's that negative sign there. So there's that plus. Equals. So we're left with 1/2 Ks1 squared minus 1/2 Ks2 squared, which is simply V1 minus V2. Same thing as with gravity. So what's that telling us? When we go to look at the energy equation, let's move this up a little right here. We have find all of the elements that you're dealing with, all of the masses, and ask the question, how fast are they going? For now, we'll call that 1/2 mv squared. When we have rotation, we'll adjust that equation. But that's what we have. Okay, these are particles, so this would be the velocity of the center of mass. All right, for every single particle, you also say, how high is it? mgh. If you have springs, you go, where are you positioned? Ks squared. Then you look at all the non-conservative work. And what kind of non-conservative work could we have? We have two more things to talk about. Let's bring this up. Friction and motors. All right, those are two common things we have to consider. And I guess just force in general. All right, equals the velocity of all the particles on the other side, the heights of all the particles on the other side, and the spring positions of all the particles on the other side. So that's the equation. So we just have one last piece to get a hold of here. And let's start knocking that off. Last thing we got to consider, let's start with friction. And let's put in a box. And let's suppose we push the box this way. And what's friction going to do? It's going to say, no, I really don't want you to do that. So it's going to, no matter where you push it, it's going to oppose it. So the cosine of the angle between them is 0, so we're left, or 180 degrees actually. So we're left with the work of friction equals minus the force of friction times the distance this box slides through. That's simple. What is the force of friction? Well, it's simply minus the kinetic friction coefficient times the normal force. Okay, then times d. Everything you've seen before. Now, let's also consider, why did that box move? Ooh, that's kind of ugly, but so there's a box. Make it black. So suppose you push that box. So this is the force you're applying. And it moves through a distance d. So it goes where you're pushing, so that would be, the work would simply be positive force times the distance. Okay. Last thing we got to talk about is motors. All right. So let's think about this just for a second. So a motor tends to turn a shaft. All right. So as this thing rotates, which would be an omega, why does it rotate? Because a torque is applied. Okay. Now, what are the units on torque? In SI, that would be Newton meters. This spinning, that's in radians, so that's radians per second for velocity, and if you looked at the position as this turns, you would have radians for theta. All right. What are the units on energy? It's also Newton meters. So is torque energy? No. This is a common mistake that's made by generally a lot of people out there in the general world. They think, oh, torque is energy. No, it's not. So here's the problem. Work, okay, is force through a distance. And I'm going to take this a little loosely. By the same token, it's torque through a rotation. So for this one, you get force times distance in a general sense. Here we have torque, which is Newton meters, through radians. Okay? So what is the work? Work equals plus or minus the torque times theta. Now why did I say plus or minus? If the torque goes this way and theta goes this way, the inner product between them is positive. So you get the plus sign. So this would be plus t theta. If the torque goes this way, and for some bizarre reason theta goes the other way, the work of the motor would be minus t theta. Now, why might that happen? Suppose something's spinning really, 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 really fast, and you go to apply a brake to stop it. Or you can even use a motor to stop it. Okay? It's spinning one way, the torque would be going the other. So whenever you have negative work, it's taking energy out of the system. Whoops, this needs to come up. Whenever you're taking work out of the system, this thing's going to slow down. Eventually it'll stop. Okay? This is going to tend to make it speed up. Okay? Now, of course, you need to balance torques and stuff and all those things, which we'll talk about later. But if you're putting torque into a system, it tends to spin that direction, unless you're slowing down, and there you have that. So, those are the basic equations. We need to look at work, energy, and power. We'll talk a little bit about some other things as we go through. But we're looking at it right here from the perspective of Eng 1082. We're going to expand that perspective with rotation and other things here later at the end of this course. But this is the basic stuff we need for now. The next thing we're going to do is we're going to start doing some problems. I'll catch you back soon. Bye.